All right. So, howdy. I am Lei, the CVA, the community volunteer ambassador for the Santa Monica Mountains National Recreation Area. I'm going to go ahead and share my screen and do our general consent statement. So, as a visible disclosure, we'd like to inform any participants that any and all Zoom series is and will be recorded. The purpose of this is to provide the Zoom series to those who participated or missed out on the session. It is also provided the Zoom session to those who participated or missed out on the session. It is also provided information for participants to refer back to. In addition to the visible disclosure, this statement will be orally stated at the beginning of each Zoom series like I am right now. I'm going to stop sharing. I feel like I would have been doing these by now. I would just like memorize it, but sometimes it's just like, I'm going to pass it on to our guest speaker today, Mike, to reintroduce himself and get started.
Well, thank you, Lei. It's a pleasure to be back with you again. My name is Mike Shaw. I'm a National Park Service volunteer. I've been volunteering now for quite some time, and it's good to see some familiar faces. So, as I like to say, for those of you who are new, welcome, and for those of you who are coming or returning, welcome back. But today, my hope is to share some insights regarding observational astronomy, and in particular, to help you maybe pick up some knowledge and tips that might help you when you're interacting with the public in regards to, commonly asked questions regarding astronomy in the night skies and what is up there and how it all works together. So really, I guess for this particular presentation, almost more than any others, if you would like to ask a question, please ask it right away. And maybe either raise your hand and I'll try to see if I can see you, or ask in the chat. But certainly while it's fresh in your mind, because we're going to go through a fairly quick series of topics, and sometimes it either disappears, from your mind or whatever. So please do that whenever you, when it comes to mind. I'm going to go ahead and initiate the screen sharing process, and that's always a little bit of an adventure. So we're going to see how this goes. Now let's give this a try. So you can see my screen there. So now we're going to try to do this, and here we go. We're going to do the, so that's working pretty well. Can you see that okay?
Yes.
Great. Okay, so look, we're going to get started. Again, please call me Mike. And one of my favorite places to start here is with this image of the Hubble Space Telescope. Now, who knows why the Hubble Space Telescope was put up into space? You weren't expecting that, were you? Well, unfortunately, I can't see everybody on my screen, so I'm sure someone probably has their hand up. As you can see, it's really to get above the atmosphere. And someone mentioned earlier today that out in RSV, it's a little hazy. We got some fall weather coming in, and it's that haze that really interferes with telescope viewing. And in fact, most observatories, Mount Wilson accepted, well, including, are at the tops of mountains to get as high, high altitude as possible to get above the haze. And so what I want to do is to just introduce the Hubble Space Telescope, and in doing so, explain one of its very first missions to sort of motivate what we're going to be doing today. So this is an image from a great astronomy textbook, Pathways to Astronomy, if you're interested in a really good resource, a reliable resource of science and knowledge, Schneider and Arnie. And if you look carefully, you can probably see the Big Dipper towards the left of your screen. And so there's the Big Dipper, and one of the very first things the Hubble Space Telescope did was to gather light from this spot for 10 days, just all at once. And that involved essentially, as you can see, as the Hubble would go around the Earth, just reorienting it so it's gathering light from the spot. Why do they choose this spot? Well, it turns out that this was a spot that no one had ever seen anything from before. And the scientists didn't know what it was there. And this was a remarkable thing, because in most scientific experiments or investigations involve, I have a hypothesis, I'm going to find this thing, and I'm going to do some experiments to find out that thing. This was a special mission. It was done by the director of the program, and the director had something like 10% of the allotted mission time. They could do whatever they wanted to. So the director said, we're going to point the telescope at this spot. We don't know what's in it. We haven't seen anything there before. Let's just see what there is to see. And this is the very first time that the Hubble's been above the Earth's atmosphere. And guess what they found? They came up with this image. And this is, to me, I'm still getting goosebumps when I see it. This is the first time that any of this stuff that has been seen. And all of these things that you see here, with one or two exceptions, are galaxies. So these are galaxies. Each one of these is a Milky Way. And, you know, hundreds of billions of stars. And, you know, if you think back to this spot in space, there are a lot of little spots like that in the night sky. And it's just incredible to think that we live in a universe that's filled with galaxies like these. And it's with this spirit, I want to help you connect with the night sky and to appreciate some of the things that are out there that you can share with some of the people you interact with. So that's just one of my favorite ways to start, because it was such an inspiring, I remember when that came out in the 90s, it was just a hugely inspiring thing. So here's what we're going to go through today. And we're going to go through this more or less top to bottom. And one of my goals with, again, the talk is to go through some topics that are, I think, important in understanding what's up in the night sky. And my approach to this is to really help you develop a really cause and effect understanding of what's up there, rather than simply saying, this is there, this is there, this is there. I want you to really understand what's out there so that you can, you know, when things change, you know what to expect. So we're going to start off with the moon. We're going to talk about the solar system, move on to the Milky Way and beyond the Milky Way. And then if we haven't answered all the questions, we're going to go through a few commonly asked questions and go from there. I will say that the this is sort of the first part of really a two-part series in a way, because Ranger Risa was able to set me up to come back in the beginning of December with, you know, month to month most common sights to see from Samo in the night sky. So a lot of the stuff we're going to have a chance to go through, connect in the next talk in December. But here's a typical, you know, roughly monthly cycle of moon phases, and we're all familiar with this. You know, in terms of what phase of the moon we are in right now. I think this is a calendar. I don't even remember what month. This was from several years ago, but as you can see, it starts off on the 1st of this month with a full moon. And then we go through a waning gibbous moon all the way to a third quarter, all the way to a new moon there on the 15th. Then we have a waxing crescent moon back to a first quarter, and a waxing gibbous moon all the way to a full moon. And this is a typical monthly cycle of events. And what I really want to do in the next few minutes is to help you understand why these phases occur and when they occur and why they're important. Because this is, I think it's one of those things that in retrospect you go, oh yeah, of course, that makes perfect sense. But a lot of times not everybody, especially the public, understands this stuff, and they're usually quite enthusiastic about learning this. So this is one of those great topics that if you were to share this information with the public, I think they'd really appreciate that. And so the first thing I want to say is that the surface of the moon that you see here in each one of these phases is the same. What that means is as the moon orbits the Earth, we always see the same side of the moon. That doesn't change. And what that means is the moon actually does rotate on its axis once a month. So as it rotates, we always have that same side of the moon facing us. And the reason for that is pretty simple. When the moon formed, it kind of had an offset center of gravity because of the Earth's gravitational tug. And, you know, I don't know if you're of a generation to remember these, but there was this toy way back many years ago called Weebles, that Weebles wobble, but they don't fall down. And it was like this toy that would be like this. You'd stand up and you kind of, as a kid, you'd push on it and it would like tip over, but then it would kind of come back. And that's the same way with the moon. And we're looking at the bottom of that, of the Weeble, if you will, for the moon. But so that's one thing. And the other thing is that the part that you can't see, the part that's not illuminated, is not the Earth's shadow. A lot of times people think, oh, that's the Earth's shadow that's on the moon. And that's most definitely not the case. When we have the Earth's shadow on the moon, that's a lunar eclipse. But that's not what we have here. This is the moon's own shadow on the moon, causing the darkness that you see here. And in fact, if you look at the 15th, you can see some detail on the moon, just like on the first. It's the same appearance. The only reason we can see that side of them, we can see that there in that particular instance, is because of light reflecting off the Earth, which is called earth shine. So you have moonshine, you have sunshine, but then you also have earth shine, and that earth shine is what is reflecting onto the moon. And this is where that earth shine is coming from. Now I have to say, I did not take this image. Full disclosure, this is a NASA image. And, it's one of the many famous images way back in the Palo days. And obviously you can actually see, if you look very carefully, I think you can actually make out, the Santa Monica Mountains, the Samo area there in Southern California. But what's interesting is that, the moon has a very similar appearance of this at certain times of the month. And, here's the moon at a particular phase. I think this was certainly taken I remember taking this somewhere in Southern California. I can't remember if it was within the Santa Monica Mountains or elsewhere in the area. But really, this diagram, I think, of course, it's not to scale, but this puts things into perspective. So over here, what I've shown is, by the way, can you see my cursor? Okay, great. I'm just realizing that. So here's the sun, here's the moon, and here's the Earth. Not to scale, but as you can see, as the sunlight shines on the Earth and the moon, the part that is sort of behind the sun, if you will, is in shadow. So the moon is casting its own shadow, and the Earth is casting its own shadow. In fact, the people in Europe and in Russia over here would be experiencing nighttime while we're experiencing daytime. Pretty straightforward stuff. Now, let's go through this in a little bit more detail. So in effect, this is the scenario. I want you to just take a minute and study this, if you don't mind. So we have sunlight here coming in from the left over here. And this is actually a globe I have on the bookshelf behind me, or somewhere. It's over on the other side of the room. And this is this model of the globe, which I actually have right here. It's my trusty moon model. I've actually shown this in a couple of the Santa Monica star parties back in the day. And what I've done here is I've shown how the moon orbits the Earth during a month. So let's say like this, if we look at this particular phase right here, when the moon is right here, how long do you think it takes the moon to get from here all the way up to here? That'd be about a couple weeks, right? 14 days, exactly, that's right. And so it takes, if it starts off here, 7 days later, it's gonna be over here, 7 days later, it's here, 7 days later here, and 7 days later, it's over here. So right around 14 days. You can see the North Pole right here, and it's offset because the Earth is tilted at 23 degrees to the plane of its orbit. Okay, so that's pretty good. Now, I want you to pay special attention to this next image, because this is actually a picture of me. It's a top view of me. I'm sitting cross-legged on the floor, and I've got a little beanie, a little cross-country ski beanie on, and I'm holding the globe right here in my hand, or the moon right here in my hand. So in effect, I'm basically holding this globe like this in my hand while I'm sitting cross-legged on the floor. And what you can see is the sunlight's coming in from the left. So that's coming in from my left. So it's illuminating my left, the left-hand side of the moon. And what I see when I look at the moon from my perspective is I see this. I see the moon illuminated from the left. Makes perfect sense. No big surprises there. Now, let's imagine it's a few days later and the moon has shifted all the way over to here. Now, as you can see, the same side of the moon is illuminated as it was before, right? Because it's, still getting the sunlight. But now what do you think I'm going to see? Is my view going to change? Well, of course it is. Now I'm going to see something that looks like this. Because the sunlight is coming from the side. And this is the key to understanding the phases of the moon. As the moon changes position as it goes around the Earth, it still always receives sunlight. It's just the part that we see changes because it's changing. How about this one? Several days later, now the moon's gone all the way around the horn and all the way over here. What do you think I'm going to see when we see the moon here? We're going to see Lay's background, which is a full moon. And that's because the moon is completely behind us and it's fully illuminating the surface of the moon. So as you can see, then this is an image from my first book on night photography. And what I did here is, there's really two main columns. There's this one, the A, B, C, D, all the way through to over here. And on each side, I show a phase of the moon, the new moon, the waxing crescent, the first quarter, waxing gibbous, and so forth. And then where is the moon around its orbit for each one of these phases. And so all you really need to remember is that the position of the moon as it orbits the Earth is the key to understanding the phase of the moon. And that's one of my main takeaways for this, for today's talk, especially the beginning part of it as we get into it, is the phases of the moon are caused by the changes of its position around the Earth each month. So that's I'm going to check that box, if you will. Now I'm going to pause for a second. I'm going to see if anyone has any comments. I don't know if I can see the comments. I don't know if I can see the comments. I don't think I can, so I'm just going to plunge ahead.
I have a question.
Oh, yes, please.
I know it's going to sound really stupid, but it's just something I haven't been able to wrap my head around. And that is that, and I think the answer is because the moon is just so far away from Earth, but this is the question. I've always wondered why people on Earth always see the same thing, because we're in different positions on Earth. Does that make sense?
Oh, it makes perfect sense. You're absolutely right. Let's go back to, let's see if I can go back to, well, actually, let me go on to this next slide. That's a great question. And let me also say that we're all friends here, and we never have to say anything. There's a different, you never have to apologize for asking a question, because that's why we're here. And if you have a question, I guarantee you almost everybody else has the same question. So I appreciate you asking the question. I couldn't tell who it was. I can only see a couple of people on, but thank you very much for asking that question. And so this is a sort of a summary subset of what we just saw. But to your point, if you look at the Earth and you look at the moon, this is the sort of diagram that, astronomers show, and it's like, okay, yeah, it's an astronomy diagram. I get it. But the key thing is that if you look at any one of these positions, 1, 2, 3, 4, all the way around, let's look at position 2 here, for example. Well, at position 2, the moon stays pretty much there for 24 hours. It doesn't move very much. It takes a week to go from position 1 to position 3. So each night, the moon moves a tiny little increment along this orbit, and that's all. So as the moon is slowly moving just a tiny little bit, the Earth goes through a complete 24-hour rotation. Now, people in South Africa, for example, are upside down compared to us, so they see the moon upside down compared to our view, and vice versa. We see the moon upside down compared to our friends in South Africa. There's an astronomer, Carol Botha, who is on one of my shows in South Africa, and she talks about the bunny in the moon. And for us, the bunny is upside down, and so we don't see that so much. And so it's just different. It's a different perspective entirely. So while everybody on Earth sees the same phase of the moon, because that's how the moon is with respect to the sun, their orientation of the moon slightly changes. So that does change, but the phase stays the same. So I'm not sure if that answered the question, but what are your thoughts on that?
Yeah, that helps a lot. Thank you very much.
Sure. I'm sure if there's any other questions, but this.
Yeah. So Mike, before you move on, there's one from your pre-moon slide when it had Hubble. So it says, are there, so it's, it's Earth and Moon. So let me just read it. In the picture with Hubble telescope, the space above the Earth appears all black, as is often the case with pictures of the Earth or Moon. Are there images of the Earth taken with a high enough dynamic range to show stars, or do they always get blacked out?
That's a great question. I am going to I'm going to end the show because that is such a great question. And I want to go back to that. And by the way, this is the sort of conversation I don't really, more than anything, I want to have with this type of, with this conversation. So I really appreciate that. And you're right. If you look at the sky up here, where are the stars? How come we don't see any stars? And it's a great question. And the answer really is, and that's the secret is in that dynamic range part of this, is that the Hubble and the Earth that we're seeing here, the space telescope and the Earth's atmosphere here looks to me as though it's almost direct sunlight, almost high noon. On the in terms of where the sun is. The sun looks like it's either directly above us or directly above us and behind us. And to get a correct exposure of the Hubble with such a bright light source, we have to sort of turn down the exposure so much that the stars just blend in with the background. And this is the same sort of observation, that there are no stars right here in the space, that is one of the prime points that you'll hear from people who have difficulty understanding that we actually landed on the moon. I'm not suggesting in any way that the person who asked the question is suggesting that at all, but I'm just making that connection because I've been asked that question. Well, how come we don't see any stars in the Apollo? And it's the same thing. It's the prevailing light is so bright that we have to bring the exposure down so we just don't see the stars. If we were to, make the exposure so that it could capture the stars in the night sky, the space station would be completely overexposed. The Earth would be completely overexposed. And so to answer your question, you're absolutely right. The dynamic range is not sufficient to capture both the dim light of the stars and the bright light of the space station. It's kind of like if you're listening to an orchestra and there's crickets chirping in the background and the orchestra is playing, you can't hear both the crickets and the orchestra. If you kind of tune into the crickets, the orchestra is going to be completely too loud. If you tune into the orchestra, you just can't hear the crickets because they're too soft. So that's another great question.
So Mike, there's actually a bunch of questions, but Greg, Arnold, Mel, do you want to ask any of them?
Please, yeah, fire away. That's why we're here.
Okay, I'll ask. So one was eclipses only happen with a full moon, right?
Yes and no. So let's go to that one. Is that the question?
That's one of them, yeah.
Okay, great. Let's see what I'm going to do here. I am going to, let's do this. Uh-oh. I have that going to do it? I lost my ability to
share?
Nope, that's what's going to happen here. Let's see here. I'm going to go to here. And let us go to, hang on just one second. So the question was about this lunar and solar eclipse, wasn't it?
So do eclipses only happen with a full moon? And then there's
Yes.
also, how do you get 2 new moons or full moons in the same month?
All right, let's do that. Okay, oh, here we go. Okay, I was able to kind of work with my system here. So that is a great question. Let's do this. I want to give a good answer to that question. And so an eclipse, and I much prefer that you ask questions like this when they come to your mind, because that is by far, to me, the fastest way to share screen. We're going to go back over here and see everybody. PowerPoint, here we go, share. There we go. Okay, so we want to go to this one right here. And let's bring this up. There we go. All right, so, I realize the link is cut off at the bottom. Here is a partial solar eclipse from RSV, May 20th, 2012. And what you see here is this dark circle is the backside of the moon. And of course, this is the sun right just here. And these were taken at 2 different times. So as the moon passed partly in front of the sun, then it eclipsed it. And that's what a partial solar eclipse. It's when the moon actually gets completely in front of the sun that we have a total solar eclipse. Now, the reason for me wanting to show this is this next slide really lays things out for you. And the answer to your question is yes, lunar eclipses only happen during a full moon. And that's the scenario shown here on the bottom. So right here you have the moon, and the moon is in the Earth's shadow. But because of where the moon is, on Earth, we see the moon as a full moon. So this is a lunar eclipse, and that's what you see over here on the right. You see this like blood red, people talk about the blood eclipse or the blood moon. That's because the shadow on the moon is kind of a reddish color. As the light goes through the Earth's atmosphere, it turns kind of a reddish color, just because that's what the Earth's atmosphere does to it. In contrast, so yes, in this case, solar eclipse, correct. You have to have lunar eclipse. Yes, you have to have a full moon. For a solar eclipse, you have to have a new moon. And that was the distinction I wanted to draw. So for a solar eclipse, the moon has to be between the Earth and the sun, and we actually see the shadow of the moon on the Earth. So hopefully that answered the question. And I think there was one other question, or? Tori, you're on mute.
Whoops, sorry.
Okay.
So yes, how do you get 2 new moons or full moons in the same month?
Great question. So this month, October, we have the only month of 2020 with 2 full moons. And it really has to do with, I'm kind of navigating around here. It really has to do with the monthly cycle of the moon. So the moon actually completes a cycle around the Earth. I think it's like 29 and a third day or something like that. So it's not exactly on a monthly basis. So it's just like the the timing. Sometimes we really only have it about one. It's really quite a remarkable coincidence. You might even argue that human culture came up with the months to correspond with the lunar cycle. But in any event, so it's just it's really a coincidence more than anything else, that sometimes some months like October of 2020 has 2 full moons or 2 new moons or 2 any of the same phases in a given month. When we have 2 full moons in the same month, then the second moon is called a blue moon, and it has nothing to do with the color of it. It's just that.
Cool. Okay, and then last one I see here is the moon rotating around the Earth's equator or over the poles, or?
Oh, that's a fantastic question. Yeah, so the Earth is actually orbiting. So here's an interesting thing. I don't have a slide that shows how the Earth actually rotates. So as the Earth, so the moon, if we consider the moon's motion, the moon is, let's call it, orbiting around the Earth, okay? So that's the moon's orbit. So this gray line that you see here, that's the orbit, that's the orbital path of the moon. But then, as I said, the moon is also rotating about its axis. Just like the Earth rotates around its axis once every 24 hours, the moon rotates around its axis once every month. And because of that, we always see the same side of the moon. And what's remarkable here is, if you look at the question is, what's the orientation of the orbit of the moon relative to the orbit of the sun? And it's almost in the same plane, but it's inclined by about 5 degrees. Now, this is most definitely, I'm going to jump around a little bit because this actually ties in pretty nicely. If you consider, well, that seems like quite of a coincidence, doesn't it? It's like, well, it's absolutely not a coincidence. And in fact, if you look at, this is obviously a schematic diagram of a few of the planets. We have Jupiter, Saturn, Mars, Earth, Venus, and Mercury, and the sun. And all of these planets are orbiting the sun, and the moon is orbiting the Earth. I haven't included that here. But what's kind of incredible, and this is something that you definitely want to point out to your the public when you interact with them, is that the planets are completely lined up. Just like if you took like a dinner plate and you put little, peas or any small objects, they're all on the same plane. And there's a very significant reason for why that is, and it has to do with, as the solar system formed and as the moon formed around the Earth, everything was a giant cloud of gas that actually collapsed into a disk that's not unlike a pizza. And you have this giant pizza in space of dust that's circling around the sun, and within the pizza-shaped cloud of dust, the planets formed, and the moon formed, and everything formed in that same disk. All of the planets are going around the sun in the same direction. All of the planets are in the same plane. It's not a coincidence at all. It's simply a result of how they formed. And this is what this image is right here is, this was from just actually July of this year, when the comet Neowise, you can see that over here. But this was one of those rare instances when look at all the planets that were above the horizon. Only Mercury was below the horizon. And I was getting sleepy, so I got impatient. This is 3:45 in the morning. But you have Venus, you have Uranus, you have Mars, Neptune, Saturn, and Jupiter, and Earth, of course, and Pluto, which is not visible. But the reason for showing this is really only Neptune. If you look carefully at this and really zoom in, you probably can't do it on this screen, but you can actually see the little dot of Neptune. You can see, this was the camera, little dot of Uranus. But really the main planets that are important to your visitors are Venus, Mars, Saturn, and Jupiter, and occasionally Mercury. This is a photograph. I don't know how easy it's going to be over Zoom, but you can see this bright dot right here and its reflection. But if you look very carefully, you can see another reflection right here. And there's a little dot right there, and that's the planet Mercury. So this is Venus and Mercury, very late. This is in the evening twilight. But before we get into the planets, so I want to go back to the moon though, because we have some more material to go through there. But let me ask the person, are there any other questions about the moon? Because those are some really great questions.
No more questions. So yeah, keep flowing.
All right, so I'm going to see before we completely run out of time. Let me see if I've got let me go back a little ways here and finish up a couple of thoughts. So we're right here. We're going to go there. See how well this works. There we go. Yeah, I love the back and forth. So please, questions like this are what we're all about. So here we are. We have the different moon phases. We have the cause of the moon phases, which is where the moon is relative to the, Earth and sun. And if we consider the full moon, as you can now appreciate, the full moon rises at sunset, give or take a half hour. This is a simple fact of how everything's lined up. Is the, if the moon is directly opposite the sun, then right as the sun is setting, that's exactly when the moon is rising. So a lot of people don't realize that you can, you ask people, hey, we're going to have a full moon in a few weeks. When are you going to go out to watch it rise? And most people are astonished when you say you just go out at sunset and you'll be able to see it. So there's that. Here's an image that I showed the last one of these Samo events, and this was the Cheesebro, Palo, Comado Canyon. There's a particular tree that positioned right in front of a rising full moon. This was quite a few years ago, but this is exactly how that works. And one of the things that this is another interesting thing that a lot of times people are intrigued by, is this thing called the moon illusion. So here it is. Here we have the moon, and you can see over here we have the moon right on the horizon. Look how big that moon looks, right? It's enormous. And then look at this little moon right here. It doesn't look so big. And then we have the moon up here. Well, it's totally an optical illusion, because if you just replace the moon with these little white circles, and then you say, let's get rid of the foreground, they're exactly the same size. And the only reason the moon appears bigger on the horizon, it's simply your brain. It's simply a matter of your brain saying, oh, well, if it's that large right next to this, which is obviously, tiny, it's got to be huge. And in fact, apparently the moon is actually a little bit smaller when it's on the horizon than when it's directly overhead, because of atmospheric optics. So, you'll get this question quite a lot, like, why is the moon so big when I saw this huge moon? And in fact, here's a question I might, since we're jumping around, ending the show left and right. This is we're all kind of friends here. So let's try this experiment out. If you would humor me for a moment and hold out your arm like so, and just estimate how big do you think the full moon is? Is it this big? Is it this big? I mean, how big do you think it is? And what I found is this, for my pinky, the moon is about half the width of my pinky fingernail. It's tiny. It's really small. And a lot of times I'm a photographer, a moon photographer, so I'll try to find something that I want to position in front of or next to the moon. So I'm constantly driving around like, is that the right size, or how about that thing over there? Because this is my sort of my scale model. So if you ask people that, most people will say it's about the size of a quarter or a dime, or back when we used to use coins. But you know, it's a really interesting point to be made that that's the case. All right, so we're sharing that screen. That's all good. Let's go on to a few more points here, because I want to go back now to this our monthly moon calendar. And you know, there's a lot more to the moon phases than simply the you know, the full moon and the new moon. So here's a shot. This is the gibbous moon. This is when the moon is more than half full. That's called a gibbous moon. It's a good astronomical phrase to toss around in casual conversation. Right now we're experiencing a gibbous moon. This is what the landscape looks like under a gibbous moon to a camera. You can see the stars in the sky. This is Joshua Tree National Park. This is a starry sky. There's the planet Jupiter, I think, hidden behind the calendar. And it's a very bright scene. I mean, it's, you know, it's easy. I know that some of the rangers at RSV have run moonlit hikes, you know, under a full moon. It's a wonderful thing to do. I think tarantulas come out at some point, or there's a tarantula aspect to that as well. But then the crescent moon, you know, sets right after the sun. This is, of course, a beautiful shot of the crescent moon right here up in the High Sierra, someplace, I think in the Palisades, if I remember correctly. This is what the crescent moon looks like. That's something to have a look at. And you can see the dates of the crescent moon occur after the new moon. So we have the new moon, then we have the crescent moon, and that slowly builds into the gibbous moon that you saw a moment ago. And then one of my favorite times of the month is the days surrounding the new moon. And this is when the moon is either below the horizon or only above the horizon for a relatively short time. So we have the new moon here on the 15th in this example, and then the days after the new moon is when the crescent moon is visible in the evening sky. The days before the new moon is when the crescent moon is visible in the morning sky. So it's, you know, this depends on which side of it you are. And these days are when you can really get the best viewing of, you know, dark sky objects like the Milky Way and some of the deep sky objects that are out there. And so, you know, if you look at the monthly calendar of moon phases, there's astrophotography there's viewing opportunities. The new moon is when you want to take your telescope out and look at, you know, deep sky objects that we'll talk about a little later. You know, the crescent moon, the gibbous moon is when you really want to look at the moon itself. The full moon's a little bright to look at through a telescope. Most people will find that the full moon, it's not a lot of detail because you don't have as much shadow contrast. So really the first quarter is my favorite phase of the moon to share with people from an astronomy point of view. And then the other thing I want to say before we leave the moon altogether is this. And this is something that, fortunately, I know this is recorded and you can come back to this slide, but I think this is a very important slide that I haven't really seen anywhere else before. This is, again, out of my first book. And you know, I haven't seen this in astronomy books or anywhere else, but especially on the bottom part here, I have an illustration of each of the moon phases, starting with a new moon, first quarter, full moon, third quarter, back to a new moon. And over here on the right is when it's visible, when the moon is above the horizon, going from midnight all the way to noon, all the way through to midnight. So as you can see, the new moon rises at sunrise because it's right next to the sun. It follows the sun across the sky, and then it sets at sunset. In contrast, the full moon rises at sunset and then sets at sunrise. And so for example, if you look, here's 3 p.m. Look at all these phases of the moon are visible during the day. These phases of the moon are not visible during the day. So just bookmark this for future reference in case you ever ask a question about, well, when can I see this phase of the moon? Or, well, the moon only comes up, sometimes people think the moon only comes up at night or something like that. And that's not really the case. So let me pause here for a minute. We've gone through a few of these planet things, but from a time check, how are we doing on time?
So we're at 12:45. I feel like since you're just taking questions throughout, I think you can probably just go till 1. And since we get to have you back, you can bookmark some stuff.
Okay, I'll keep going a little long. I'll leave a few minutes towards the end, especially because I want to have okay, I'll keep going then. So if we actually, let's go back here to our outline of the talk. Whoops, went one too far. So we've talked a little bit about the moon. So that's pretty good. We've covered a little bit of the solar system. I want to spend a little bit more time in the solar system, but then I want to go through the Milky Way, maybe one particular concept with regards to the Milky Way that I think you'll find of interest. So we've talked about the planets. Here's Venus and Mercury. Here's Saturn. I'm sorry, here's Jupiter. Saturn's right next to it, but Jupiter is a marvelous, this is one of the great objects to observe through a telescope. Watching the moons of Jupiter is really, really something to see. And, you know, the brightest planets that you're going to see from where you are Venus, Jupiter, Mars, and Saturn, and the Earth. And it's possible to see Mercury in the twilight. It's pretty challenging though. And then Uranus and Neptune, you're really going to want to use a telescope for those. Now, this was a planetary transit of Venus back in June of 2012 at RSV. And we don't have one of these coming up anytime soon, but this is certainly one of those key events that when it happens, this is the planet Venus right here, and it's right across the face of the sun. This is really a fun thing to watch. All right. Now, I think I want to jump around here a little bit because there's a particular point I want to make here that I think I don't want to wait till the next, oh, here we go. We're coming right up on this. So let's just start right here. And this is only going to be a few slides, but I think it's, this is such an important point that I think it's worth going through here. So here we have the sun and the Earth's orbit, and all these blue things are stars. So this is space. We're outside of the Earth's orbit. Here's the Earth's orbit right here. Here's the Earth. And this yellow arrow right here, this is pointing at the sun. So this blue half of the Earth is experiencing daytime, and this white half of the Earth is experiencing nighttime. Makes sense, right? So that's all good. Okay. Now, here's the thing. So those people who are on that side of the Earth, this is what they see. They see these stars at nighttime. Makes perfect sense. They can't see these stars because it's daytime for them. The sun is in the way. But at night they see these stars, but they can't see these stars. Now, as the Earth rotates each day, what happens is within the stars they see at night, these are the ones they see, you know, around sunset. And then the Earth rotates, they see these stars around midnight, they see these stars right before dawn, and that works out pretty well. So that it's kind of like the Earth is this restaurant that rotates, and you get this sweeping view of the cosmos. So let's see if this plays. Okay, so here's a little time lapse up in California Sierra showing the Milky Way going by. You've probably seen time lapse, but try to imagine if you can that the Milky Way isn't moving. It's the Earth that's moving. So we're actually rotating. We are rotating past this during the Perseid meteor shower. We are actually rotating past the night sky. So that's kind of a neat perspective. So to recap then, when we see these stars, those are the stars that we see. So that's fine. All right. So what does that mean? Well, that was when the Earth was at this particular location. Let's say hypothetically that was in January. Well, guess what? 3 months later, the Earth is going to rotate over here. Remember, because it takes like a whole year to go around the Earth. Now, when the Earth is in March, it's moved. So at nighttime in March, this is what we see in January. But look, this is what we see in March. We see a totally different set of stars, completely different. And it's entirely because the Earth is rotated around the sun. And this is why, this is midnight looking due east in October and in May. We're just looking at different parts of the universe. Even if we look at the same direction, same time of year, all that sort of stuff. So I wanted to go through that with you as a, as kind of a, oh, that's interesting point kind of thing. So Tori.
So yeah, something came in. Why does Pluto orbit the sun in the opposite direction? That's one.
So Pluto's an interesting thing. Now, I'm going to end show so we get the whole visual here. So, oops, I ended show, and I'm going to bear with me for 1 second. The little stop sharing button kind of jumps around the screen. So Pluto is, so the solar system is the solar system. You have the sun, you have the planets. Pluto, I didn't know that Pluto rotated in the opposite direction. That's interesting. I'll have to, so that's a cool thing. But Pluto is not considered, well, it's considered part of the solar system neighborhood, but it's not, as you know, considered a planet. It was demoted. It's kind of a sad story because of the requirements to be a planet, and Pluto only meets 2 out of the 3 of those. But the curious thing about Pluto is that if you look at the plane of orbit of the of the planets, Pluto is at a much different angle than the solar system planets. And partly that's because of its origin. We have there's this Oort cloud, there's a Kuiper belt, there's a range of different objects outside of the solar system. And one of the premier discoveries of the Hubble Space Telescope is that the Hubble was able to image these objects beyond the solar system and discover that there are literally, tens of hundreds of thousands of these objects like Pluto that are similar to Pluto that we just hadn't seen before because they're just a little bit smaller. So one of the dilemmas was, well, do we have to include all of those things as planets, or do we somehow separate Pluto into its different category? And that was, after a lot of back and forth, that was one of the decisions. So Pluto going in a different direction is because of that not same origin as the planets within the solar system. So that's an interesting point. So I'm glad you pointed that out. Interesting. Yeah.
Is it a coincidence that the relative size of the sun and moon are the same, or is there a physical reason?
100% coincidence. One of the most remarkable coincidences. I'm glad whoever asked that. It's a complete coincidence. It's an amazing coincidence because it's because of that precision in diameter. We have the phenomenon of a total solar eclipse where we can see the corona of the sun in such exquisite detail. Here's an example of a case where that's not the same. If you look at the planet Jupiter, it's very common to see the shadows of Jupiter's moons on Jupiter. And in that case, the Jupiter's moons are much smaller than the planet. So a solar eclipse on Jupiter is, you just wouldn't see that same matching of the Jupiter's moon with the sun. So it's a very, very happy coincidence. Great question. So if anyone asks that, purely a coincidence, no physical reason for that.
Cool. Okay, the purpose of the new Webb telescope.
Well, boy, that's a great one. So the James Webb Telescope is a telescope. It's it's planned for launch. It's made up of lots of smaller mirrors put into a large. So basically, any telescope, you want to have as big of a telescope as you can. It's kind of like if you think about your ear gathering sound. If you go like this, you can hear better because you're gathering more sound. And it's like that with telescopes. I mean, basically, the larger the telescopes, the better. The telescope array that recently imaged that supermassive black hole last year was actually set up of at least three telescopes at different points on the Earth. So basically, the Earth acted like as a giant telescope. The only way to do better than that is to go outside of the Earth. So the James Webb is really to look at all kinds of astronomical research. Dark matter, dark energy. The origins of the universe. Just all kinds of astronomical features. Its ability to capture. So essentially what happens is, if you think back to where we started today with the Hubble Space Telescope, just, fishing in that spot in space, one of the things is that one of the most important questions in astronomy right now is how close to the Big Bang can we get? And in other words, what happens is when if you look at objects that are essentially the most distant from us, because they're the most distant from us, their light has had to travel the farthest to reach us. And because the light has had to travel the farthest, the light that we receive from them, I'll go through this next time, is very old light. So because that light is so old, some of that light actually started shortly after the Big Bang. Now, because it started so long ago and it's so far away from us, it's very dim and faint and is difficult to detect. But telescopes like the Webb telescope are able to capture the very dim light and give astronomers clues as to how the universe formed, and thus what's the fate of the universe and things like that. So it's a very exciting instrument when it comes online.
Wow, I feel like nothing can stump you. Maybe we need a fate of the universe talk too. Let's not
Well,
do that one.
There are many questions to stump me, but yeah, they go beyond the topic of the moment. But
Okay. Okay, so in reading about the Nobel Prize for Physics this year, it was mentioned that there is a black hole in the middle of the Milky Way. Do galaxies all rotate around black holes?
fantastic question. You know, that's not settled for sure just yet, but the prevailing wisdom is that yes, you know, as far as astronomers can tell, and the question then becomes, did the black hole form and then the galaxy formed, or did the galaxy form and then the black hole? So what is a black hole? So essentially what happens is any star that, so the question is, in my opinion, yes. I can't say that there's a bona fide 100% on that, but yeah, I think so. So that's a safe bet. And what happens is the sun is the gravitational anchor for all the planets in the solar system. So if you think you're spinning a ball around you're spinning anything around your head on a string, you're pulling on the string to keep that thing going in a circle. If you let go of the string, it would go off in a straight line. So the sun is doing that with the planets. The sun is pulling on the Earth. The Earth is moving at a huge velocity, but because of the sun's gravitational pull, the Earth moves in a more or less circular orbit, just like all the other planets. Now, the sun formed from a huge interstellar, cloud of hydrogen, back in the day. Depending on how big, just like in a thunderstorm, raindrops form. So if you think of a thunderstorm, raindrops form, you get rain. If it's a huge thunderstorm or a cloud, you might get bigger raindrops. And it's like that with stars. If you have a small cloud of gas, you have a small star. If you have a large cloud of gas, you have a big star. And if you have a big enough star, when the star reaches the end of its life and it collapses, it forms a black hole. But you have to have a big enough mass of material, of hydrogen, to cause that to implode into a black hole. And the reason it's called a black hole is it's got such a profoundly strong gravitational pull, it actually warps the space around it. And I'm sure you've heard, as light travels near a black hole, it actually goes into the black hole, and it's material is going into the black hole faster than light can come out of it, as crazy as that sounds. So it just isn't visible to us, and it becomes there's nothing to see.
It does sound crazy. And this question too. So could it be that black holes are responsible for the equilibrium of the universe?
Great question. So the equilibrium of the universe is that's a very profound question, because one of Edwin Hubble's great discoveries back in the last century is that the universe is not static, but it's actually expanding. And, this was not on Einstein. This was not consistent with Einstein's theory. And this is one of his, there's a phrase for his most colossal mistake, which is like, that's not a terrible batting average. But so the basic idea is that, I guess I would say, I don't know that the universe really is in equilibrium in the sense that it's a very dynamically evolving thing. It's evolving very slowly from our point of view. We have a hard time, detecting any change from our human scale of observations. But, it would be interesting to have a thing on, the fate of the universe, because it's certainly, as objects expand, and it's important to recognize, without running out of time too much, that objects aren't moving through space. They're actually just expanding. Just like if you blow up a balloon, the surface of the balloon just gets bigger and bigger and bigger. So from that point of view, the equilibrium is kind of, it's a steady state of expansion, even though it's accelerating. But one scenario is that in the distant future, things have expanded so much that we actually don't see any stars in the sky, because they're just so far away, their light just doesn't reach us. And it's kind of one of those weird, astronomers are really good at coming up with these apocalyptic, doomsday scenarios. But certainly, the black holes are it's just one of the natural phenomena that litter the universe along with everything else. They're fascinating, and there's a lot of things that astronomers certainly don't know. Dark energy and dark matter being premier among them. And that's one of several of the topics the James Webb Telescope is seeking to understand. So, there's a lot that's unknown, honestly.
All right, I think we have one or two more questions. How much bigger do scientists believe the universe actually is compared to the known universe?
Pass.
We got you.
Stuff. No, I don't know. That's a great question. I wish I had something intelligent to say about that one. Before I just dismiss that out of hand, I didn't mean to be too facetious about it, because that's such a great question. So the visible universe, this is the light that we can see that has reached us since the Big Bang, and there's sort of a limit to that, and there's it's like, well, a minute ago you said that you can see all the way back to the Big Bang, and now you're saying that there's a limit to how far back you can see. And this is one of those things that when it comes to this edge of understanding, it's an edge of understanding, and that's one of the things that physicists just are still seeking to understand right now. So that's a great question. I wish I had an answer to that.
All right, this last one might be a suggestion unless you've seen it, but there is a public television series called Ancient Skies, which talks about how societies and civilizations tried to understand what they were seeing in night skies. Have you seen it? No?
No, that's
okay.
Yeah.
So Ancient Skies.
Thank you.
Cool.
Yeah,
Go ahead.
I was the one that asked the question. Yeah, I think it just started, but yeah, really fascinating, because the most recent programs talked about just how like the Ptolemaic sense of what what was in the night sky versus the Copernicus, and I think it was Da Vinci that got under house arrest for the rest of his life, because he was the church and
Galileo.
ancient societies were saying there were gods that were dragging the sun across the sky, or that kind of thing. But it was just very interesting on just how much they suppressed scientific analysis of what was really going on out there, and it got pretty ugly. A lot of people got burned at the stake, and other things like that. But yeah, I've just recently been seeing it on public television. There's several series, and apparently it's still going on.
Well, Mel, I'm glad I haven't seen that. I'd be very interested in that, because there's so many different angles to the history of all this, and without getting too deep into it, but I mean, a lot of what you're saying is almost as true today as it was back then. So I'll definitely have a chance to check some of that out, because that's a fascinating. It was when people really start to connect the dots as to how understanding came to be. It's not a straight line, and it's fascinating to see how that happened, and how different scientists developed the understanding, and then some of the obstacles they faced in society in communicating that understanding. So definitely, I'd love to see that. Thank you.
And one other quick interesting thing that I've always dismissed astrology, and I still dismiss about 99% of it in terms of controlling your life. But in one of the programs, they did mention why the zodiac signs are so prominent, and it was something about, you might know this, Mike, as the Earth moved and moved through the galaxy, there were certain clusters of stars that they saw, and apparently it was more a case of, oh yeah, well, as the Earth rotates and does its yearly thing, you see certain star clusters. So that's why the zodiac signs are so prominent, because I would tell people, a handful of stars out of hundreds of billions, and you think those somehow control your life. I'm like, you might as well go find a grain of sand on a beach, cut it in half, and say that one controls everything that's going to happen in your life. But I found that interesting, that there was some logic as to why the zodiac signs are so prominent.
Oh, no, Mel, you're absolutely right. In fact, I have a short explanation for precisely what you're talking about. And so I don't know, I don't think there's time to go through that today, but we'll certainly include that on the next talk, because you're absolutely right. Basically, it's just where, I'll say it's like right now, for you, it is shortly after 1 p.m. If you were to look at the sun right now, and you were to somehow get rid of the blue sky so you could see the stars around the sun, those stars, whatever constellation that is where the sun is in that constellation. So that is the current zodiac sign of that time of year. And so basically all of as the sun moves, as the earth goes around the sun appears to trace out this line in the sky called the ecliptic, and the zodiac are the constellations along the ecliptic, and there's nothing more than that. So you're quite right. I got at least a little schematic that'll lay that out. So great question. Thank you.
Thank you, Mike. We're lucky to have you once, let alone all the series that you've offered to come back. We have lots of people saying, awesome, great, keep coming back, gotta go, but lots of exclamation points. So
thank you.
Yeah, thank you. If your question didn't get answered, please hold till next time. And that's it. Thanks, Mike.
Well, great. Thanks so much again, everybody. And certainly look forward to seeing you all again. Thanks again.
All right. Bye.
Thank you.
Bye, everyone.
Bye.